Hey, how's it going? I'm just checking our stream, making sure that we have good internet connection. Looks like we have good connection and we have sound. Cool. All right, so one thing that I wanted to show was if you're running into some trouble like with NanoHub or yeah, specifically NanoHub in this case, but it could be like any kind of Jupyter problems, like if you're running Jupyter on your own computer or you're trying to run it somewhere else. So right now it's like you can't, it's telling me that the connection failed. And if I look up here, it says that it's not connected. I can try to say like, okay, reconnect to this kernel, like clicking this button, but it's still telling me that it's not working. So when I say restart, that one, it looks like it worked, but if I come back up to the top, let's see if it'll actually run. Yeah, I get this star. So the star means that the server is trying to run this code, but right now it can't do that. So the trick for this is just make sure that I'm actually logged in. So I'm going to click on this dashboard up here, and it's going to bring me to here, and it's up in the top right, it's saying like, hey, you haven't logged in yet. So I'll just log in. Let me get password. Paste it in. Okay, so now it's running, and if I open this thing up again, it's gonna create a whole new session, but I don't need like a new session. I can just open here, or I can even just come back to this tab that I was just working on and just say restart. And it'll say restart, and now, oh, still doesn't work. Doesn't want to work. Yeah, because it's showing me this like broken kernel. I thought I could just maybe reconnect. Still not connected. Okay. So for some reason, it's just not working. But I can jump in here, say open. I think I can. I'm pretty sure. There we go. All right, it just took a second. So we'll leave that site, close this one. And when I click that file open from this main page, well, and at any Jupyter Notebook page, then I can look at what files I've created. So I have some untitled ones here, like this homework 1 that I was working on. And now we're here in homework 2, working on this. And now when I run code, it actually runs. And I'm gonna save a copy here. Let's make a copy. And we'll call it. You don't have to make a copy. I'm just doing it because I end up with multiple versions of this all the time. All right, so now I have this head of transistor data, and I saw some people having trouble, like, so as I was reviewing this homework, some people were having trouble like locating this file. So you're getting something like this, like cannot open this file, no such file or directory. And if you're running this on your own computer, that might be because you didn't download this transistor data. That I'm not saying like you didn't download this specific data, but like this file does not exist, and that's what it's saying. Like it can't open it because it's not where you're telling that thing it is. So you can use like you can list what files you can open, like this. ls will list everything. I could list everything in that data folder, and it'll show me all of these CSV files. And if you can't find, like, here, I'm gonna misspell data so that it says, like, if you can't find a data folder, then it's probably just not there. And you can get there. So if you go to our main computational mechanics and you have your own fork of it, so everybody has a copy of this repository, but you could come in here. We're using two of them. Right now we're using this, well, we're using a couple of them. Beers CSV, the transistor data down here, and also this, I think it, yeah, primary energy. So you can click on these, and you could click this download raw file button, and that'll get that data onto your computer if you're trying to run this from somewhere else. But you got to keep track of like where things are. So that was the first thing that I noticed. Yep. So once I have that, then I think most people, once they were able to load this in. All right, so we'll call this data is P. I guess I should call it like transistor data. And now I can look at what this data frame looks like. And when I'm looking at this, there are 186 rows. It's only showing me 10 of them. So it's showing me the first 5 and the last 5. If I want to look at all of them, I think usually there are ways that you can force it to like print out all 186 rows, but it's usually not worth it to do that in a notebook like this. But the main thing that I'm trying to do in this first exercise is figure out like how many missing values are there. So if I just look at the MOS transistor count, and if the tab complete, I think is one of the best features of like development environments, because I'm always misspelling things. So as you start to type out MO, you hit tab, and then it'll. And here again, I can see that there are at least 2 missing numbers. And is, I think it's is NA. Okay. So for pandas data frames, it's is NA. If you turn it into a NumPy array, I think it's is NaN. A little confusing, but so if I'm just trying to figure out, is that value missing? I can use this function and say, if it's missing, it'll show me a true value. And I could sum up how many missing values there are. And every true statement is a 1, every false is a 0. So all the zeros add up to 0, all the 1s add up to the total number of missing values. So I have 7, and I'll divide by length of my data set, and I know that 3.8% are missing, 7 out of 186. Cool, and now, so this part, if you were having any trouble, if you click this link, it brings you back to the reading, and so there's kind of like a step-by-step, like describing all the steps of how to get to this bubble plot, and then finally this one. And then if you label them, then it makes it even a better comparison between the two. And the real difference that we're trying to do here is that instead of coming all the way back up here, instead of dropping these NA values, we're going to fill NA values with 0. So we're, instead of beers clean, we'll have like a beers filled. And that's really the big difference between the two scatter plots. So we're not trying to make this one. We're trying to build this scatter plot down here. And if you want, you could copy that image address. And paste in that this is the original one. And one thing to keep in mind is look at the scale. When I ask you to compare what differences do you notice, take a look at the scales, because in the whenever you fill those zeros, it's going to bring like this American double down to like 70. Like all the averages drop by a lot, for something to notice as you're taking a look at this. Cool. All right, so I have this transistor data set, and I want to look at like just the 2017 data. So I can say trans of date of introduction is 2017. And that's just showing me what happened in the year 2017. I think some people tried to use like this, and you end up with an empty data frame, because this, whenever I'm using this true false, so it's Boolean indexing, if I'm trying to use this true false thing and there is no true case, then it's going to return the same data frame but just 0 entries. So at least the way that I have it, all of these date of introductions are integers. So I can plug in that 2017 just like that. So we'll call this like T2017, like that. And now I can do a plt.boxplot of, and all I need is this MOS. Oh yeah, it's not defined yet. And now it'll show me the transistor data. And really everything's like, there's lots of change, lots of stuff that happened in this year 2017. And if I want, I could do this like divide by 1E9. Sorry, billions. So it was like between 5 and 6 billion transistors in the year 2017, with as many as like 19 or 18 billion. Cool. So that was kind of, and then there's also like getting the quartiles. So I could grab this same kind of data. And np dot, I think it's quartile, yeah. So 4.8 billion, it's like the, yeah. And that's what these little values, that's what these parts of the box are. So here's 7.25, there's my 5.4, and here's my 4.8 down there. Cool. Now this part can be a little tough of like trying to label trying to like color these data sets according to the designer. So usually what I do to start is just figure out like, how do I plot this data? Like what does the data look like and how do I start doing things from there? So let's try making a semi-log y of my date of introduction versus the MOS transistor count, and we'll just make a whole bunch of squares. And if I look at all this data, just nothing's labeled. Well, technically everything is labeled, but it's all the same label. Like it's all blue. So whether it's IBM, Intel, Nintendo, Amazon, like they're all just the same color. So I've accomplished part of the task. Everything's plotted. They all have their own color. It happens to be the same color. Now I want to figure out like, all right, how do I start designating like what IBM was doing versus what Intel and all these different designers, like how are they working? And I saw like some people, it seemed like there was some work with like AI kind of stuff. So let's pull up ChatGPT. Let's plug this in. So I'm just taking this this problem statement and using that as my prompt engineering. And let's see what I get from. Yeah, so I saw like this was some of the code that I had noticed. It's like file path equals this, and then data equals that. Okay, well, yeah, it's not going to have that CSV. It wants me to upload that data. I don't really feel like doing that. So it's trying to run this code. Ugh. All right, all right, we'll try it. Let's see. So we'll come in here, cancel that. And we're going to go into data and we'll grab this transistor data, download it. Now we can upload it. You know, the modern conveniences, right? Transistor data. Oh, I guess it's in there twice. Let's get the original. Okay, so it actually created a mount path for it, read the data in. It's telling me what it thinks the data is, so let's try that. And it's using Seaborn instead of Matplotlib. Seaborn is fine. There's nothing. It can be a nice visualization software. Most of what Seaborn does, Matplotlib can do too. There's some stuff, like this is kind of cool. Joint plot. This might be kind of hard to do in Matplotlib. And really, like these are way better examples for running this. And sometimes ChatGPT does check the actual gallery and tutorials of stuff, but if you're trying to get a better plot, it's usually better to start with like an example in here, and then like copy this code and work from there. But anyway, we'll stick with ChatGPT, see what it's giving us. And here, it's okay. Semi-logarithmic y-axis. And right now it looks like it has the same kind of problem that usually I run into, where it keeps repeating the color scheme. And the reason that it's doing that, designer tab 10. Oh, that's where the tab 10 came from. I'm like, who picked that tab? Like, who found that tab 10 palette? Hue is designer, palette is tab 10. What is a tab 10 palette? I think tab 10 means that it's 10 different values. Circular, coloring, set to, paired, rocket, Mako. I'm trying to find like a better color palette in here. Here, let's just so remake the plot using a different color for each designer. And some of the things that kind of have to happen here is that you have to create a unique set of designers. So as I'm looking at this data, if I look at all of the designer data, if I grab values, I think it'll show, yeah, if I ask for the values, it creates a NumPy array, and it's going to show me everything. And you can see like Intel keeps popping up over and over. So this is not a unique set of designers. This is saying like in the year 1965, Intel made 2 different things, and then 1966, and so all these different things. So really what I want is the unique set, and open close, the unique set of designers, so that Intel shows up once, IBM is there once, Hitachi, Fujitsu, like every designer is only in there one time. Even, I mean, IBM is in there twice because there's IBM Apple versus IBM, or IBM Nintendo, sorry. But that's okay. And then let's see how it did here. We'll copy this over. Let's see how it worked. So it's using a color palette. And I guess I have to import SNS, right? Oh, data cleaned is not defined. Let's just. Data is trans data. Let's try that. What? Oh, all right. How does this look? Now all of these have at least slightly different colors. It's not perfect. Like Intel and Garrett look kind of similar. I don't love the layout. Bbox to anchor. So this is looking at this legend. I don't know. If we're setting Bbox to anchor, we don't need to say, and we'll say n calls equals 3, like that. All right, control matplotlib change number of legend columns n calls. That's what didn't I put n calls? What did I say? N calls. What? N calls equals. So what's the problem? All right, so change number of legend columns to 3. So it's going. NCOL? Is that my problem? There we go. That's a little better. Looks a little better, right? Taking the designers and putting them into 2 columns like that. And it's on the log scale. Cool. I don't love this. The title is transistor count over time. I mean, it's just labeling the and we know it's on a log scale because we don't need to say that it's a log of the transistor count if the scale is already shown as a log scale. Let's put date of introduction. Of transistors increasing over time. Yep. And so this is one way, like in this case, what I'm doing is creating a scatter plot, and this little piece of code here is changing this y scale from a linear scale. So here it's starting at 0, going up to 4 times 10 to the 10. Well, 0 times 10 to the 10 up to 4 times 10 to the 10. And I can change that scale by saying like, all right, put it on a log scale, just like that. And now it kind of runs along here. Yeah, and increasing over time. Per semiconductor. Come on, man.